Hello! We are here in my sunroom, and today we are going to talk about specific comparisons of means or post-hoc testing following ANOVAs. So, welcome. I'm here with Morty. I think he's going a little stir crazy, but it's going to be okay. So, let's just get started. This is still chapter 15 where we talked about analysis of variance. These are tests that you would run following a significant analysis of variance, a significant F statistic. All right, so let's jump in. First, you may appreciate this meme. All right. Ooh, you know what? We should still do our meditation. Okay, here we go. Ready? Everybody, let's follow our breath for 1 minute. Okay. So on Thursday, your video for that next class will be the tutorial video about how to run ANOVA and Posthocs in R. So the ANOVA tutorial is already up. The Posthocs video will be up sometime before Thursday so that you can actually ask about it when we are on our live Q&A call on Thursday. Woo! On Google Meet. All right, so let's jump into post hoc multiple comparisons. So you have a significant F statistic. If you have, remember, if you have a significant ANOVA, that doesn't mean that every single group is different from each other. Remember we talked about how ANOVA, a significant F statistic, and p-value only tell you that there is a difference. It does not tell you where the differences lie. Multiple comparisons are what tell you where differences lie, and there are multiple ways of going about that. Okay. The issue with multiple comparisons is that you inflate what we call your experiment-wise error rate, also called your family-wise error rate. So you might say, well, why can't I just do, a bunch of t-tests? I have a significant ANOVA, now I just want to compare two means over and over for different, say I have, 4 groups, and now I just want to compare group A to B and A to C and A to D and so on and so forth. Well, what you're dealing with is that is a family of tests, essentially tests on the same data set, you might say, and you are dealing with an experiment-wise error rate. So basically, the more tests you run, the higher your likelihood of committing a type 1 error or a false positive, okay? Hi. So if your overall F statistic is not significant, you don't have to watch this lecture because it's over. There are no differences, okay? You don't go forward. Do not pass go. Do not run the Tukeys. You're like, I don't know what a Tukey is. Well, you'll learn. You're going to learn today. All right, so if your overall F is not significant, you don't have a significant p-value, then you're done. There are no differences. However, if you do have an overall significant F statistic, then you can use post-hoc testing to help you spot the difference. Where are the differences? That's what this is all about. Okay, so like I just said, a family of tests essentially are like tests on the same data set, or basically the data you ran the ANOVA on. That's going to be your family of tests, okay, your potential family of tests. And you really, all of this is decided a priori. So while you're designing the experiment, before you're to actually running the statistics on the data, you've decided a priori, beforehand, before the fact, that they're using, these data are my family of tests, okay? These are the levels of my independent variable, and these are my response variables. And this is what I'm interested in, okay? Cool. So within those tests that you can run following a significant ANOVA, you have planned and unplanned comparisons. So planned comparisons are what I'm going to show you first, and they test among combinations that you decide a priori. So when you are designing your experiment, you say, okay, if my ANOVA is significant, I'm really only interested in comparing, well, these two groups and then this group with this group over here. But other comparisons I'm not really interested in. Those are planned comparisons. And they're powerful, and that's a good idea to do them, but there are certain rules that go along with that. And I'm going to teach you that in just a second. So that's one kind of testing, is planned comparisons. The other is unplanned comparisons. And those are a posteriori tests where you didn't decide before your test, before you got your data, how you wanted to test everything. And maybe you're interested in all possible combinations. If so, then post-hoc tests such as Tukey's test or Bonferroni adjusted t-tests might be fine for you. Okay, and we're going to go through those as well. One thing that you have to understand, though, is the post-hoc tests, as I said before, you incur a penalty. So you have an increased probability of type 1 error if you just go willy-nilly doing a bunch of t-tests. Okay, now, planned comparisons do not have this issue, but unplanned comparisons do. Okay, all right. So here is how you actually would calculate your family-wise error rate so that you can understand this. So remember, type 1 error rate goes up with multiple comparisons, particularly and specifically with a posteriori comparisons. So these are comparisons you did not plan beforehand. Okay, to calculate that error rate, that is equal to this equation here, which is 1 minus the quantity 1 minus your alpha, significance level, raised to C, which is the number of tests that you're interested in running. Okay, so this table is from Quinn and Keogh, one of our optional textbooks, and it's showing you here essentially how your family-wise error rate goes up with the number of tests. So with just a few tests, your family-wise error rate is still higher than I would like, but it's not terribly high. But as you incorporate more tests, that probability of a false positive goes up, and you want to control that. That puts your results, makes them suspect if you don't abide by these kinds of rules and really either try to control or account for experiment-wise error rate. So let's talk first about planned comparisons. What planned comparisons do essentially are partition the total variance in your data set. Okay, so remember we talked about analysis of variance, right? And you have your total sum of squares, which is the total variation in your data, that is the sum of your sum of squares from your treatments, which is the variation explained by your treatments, that between group variation, right, or the among group variation, and then that added to your residual variation or unexplained variation that we would that we would say was sampling error, right? Okay, so that's basically what we're doing here. When you do planned comparisons, you have to make sure that they are orthogonal. And I'm going to show you how a planned comparison is orthogonal because you actually have to code each contrast. I know you're like, what? Don't worry, it's actually not that hard. And yeah, there are just certain rules you have to abide by. But basically, you can do non-orthogonal planned contrasts. They're just not as powerful. And so orthogonal contrasts are what people prefer to do. And I think that you will always, if you're doing planned comparisons, I would say do orthogonal contrasts. Okay. All right. So you code your contrasts to ensure that they are orthogonal. Okay, so basically all you're going to do is assign weights to your groups, and that shows what the contrasts are. You create a table. We're going to do a couple of examples of this so that you understand it, because I'm going to ask you to ensure, to check to see if certain contrasts are orthogonal, or come up with your own orthogonal contrasts. Before our test next week, I'm actually going to put up a few examples that you can do, and you can test to see if they're orthogonal to give you some practice, and I'll have a handout posted to Schoology that kind of goes through it as well. Okay, so here are the rules. First, and here is a nice little example. Okay, so here is the table where they have checked the contrasts. Okay, so this is dose of puppies. Okay, I thought it was cute. So, dose of puppies here, all right? All right. Cool. So, sorry, I'm here. So, we're doing two contrasts. Here's the thing, when you're doing orthogonal contrasts, you're going to do P minus 1, P being the number of groups in your ANOVA, P minus 1 contrast. So here they had 3 groups, so 3 minus 1, they're doing 2 contrasts. If I had 5 groups, it could be 4, okay? So groups coded with positive weights are compared to groups coded with negative weights. So positive weight, nope, positive weight, yep, nope, it's negative. Sorry, y'all, it's small on my computer. So -2. So here what's happening is they're comparing this group to these two, okay? All right. So comparing control to these two groups, okay? The combined means. So that, comparing negative to positive. And here this is pretty simple. You're just comparing 15 to 10. And they're not concerned with the control group. And when that's the case, if you are not involving a group, then for that contrast, you code it as 0. Okay? So we're comparing -1 to +1. If we're comparing this to these two, it's -2 and then a +1. Because you're comparing this to these two. Okay? All right. Whereas this is only being comparing to this one, right? Here. All right. The sum of the weights for a single contrast must be 0. So what that means is if you come across in the columns, your control is -2, plus 1, that's -1, and plus another 1 is 0. All right. And as we go here, 0 minus 1, there's -1, and then that goes to 0. So the sum of the weights for a single contrast, which is basically your rows, is 0. It has to be 0 to be orthogonal. The last rule is that to be orthogonal, the sum of the products of the coefficients within a group must be 0. Okay, that's not even hard. You can do this. So look down here. So what that means, let's just break it down. So the products of coefficients within a group. So you're just multiplying this way, up and down. So -2 times 0 is 0. Okay. -1 times 1 is -1, and +1 times +1 is +1. So here you have 0, -1, and +1. Those are the products of your coefficients, and then you sum them. So 0 minus 1 plus 1 is 0. So these are orthogonal contrasts. Okay, so let me just say those rules again. Compare positive weighted groups to negative groups. And you're choosing what you're comparing. It's just saying when you're comparing this to this, that's how you code them, positive versus negative, okay? If you're not using a group, it's a 0. When you're going across the rows, the sum of those coefficients, the weights, must be 0. And then as you go down a column, you're going to multiply. So you're going to get a product of those column coefficients and then add them across. And that must be 0. Okay, we're going to practice this, so don't worry. Here's another example. Just go ahead and just look here. So here I have 5 groups. So if I'm comparing this group to these, okay, then this would be plus 4, because I'm comparing this group to these. My dog just made a really weird. My dog is dreaming. Now, where is she? Okay, my dog is dreaming. I hope you could hear that. It was adorable. Okay, so here, positive 4, because we're comparing it to each of these, but these to only this, right? So negative 1, negative 1, negative 1, and negative 1. Okay, so the sum here is 0. And then if I'm comparing this group here to these three, okay, so I'm giving it a positive weight and I'm comparing it to these three, I'm going to each give a negative weight. So, and I'm not interested in this group during this comparison, so the sum across here is 0. Now, let's do the product. 0, positive 1, positive 1, negative 3, positive 1. So the sum would be 0. Okay, great. So, because it's negative 3 and then plus 1 on each of these, so 0. Great. So those are orthogonals. But let's do an example. Okay. So let's say we're comparing the popularity of 3 subs, BLT. If you hear some stuff, it's my kid and my dog. The BLT, meatball, and spicy Italian. Before your survey, you know, so this is beforehand, you know you're going to be interested in certain contrasts. And there are certain ones you're just not going to care about. That is the case where you will do planned comparisons. Okay, so you know you want to compare, I'm writing this down for my own edification, meatball versus BLT and spicy Italian, and BLT versus spicy Italian. Okay, so let me put this on our little blackboard up here. So, a key. Let's create a table. So let's say we're going to do meatball, and here we're going to do BLT, we're going to do spicy Italian. Yeah. All right. So I'm only interested in these two contrasts. So contrast 1 and contrast 2. You can really only do 2 contrasts here because you have P minus 1, right? 3 groups. 3 minus 1 is 2. Okay. Oh, I coughed earlier and was like, oh my gosh, do I have the coronavirus? So, I better not. So, we're comparing meatball to BLT and spicy Italian. So that's going to be plus 2 to BLT and spicy Italian. Okay. And then here, I'm not interested in meatball. Sorry, meatball. I don't really like the meatball. I think it's my husband's favorite. Oh. You like the meatball? I just, okay. And then, oh yes, BLT, so plus 1 versus spicy Italian, minus 1. So let's check here. For sum here, across is 0. Yos means and 0. Okay, so now let's do the sum of the products of the coefficients. So here, 0. Here we've got negative 1, and here we've got positive 1. So that also equals 0. So these are orthogonal contrasts. Now, I know all of these examples are with just 2 levels, 2 contrasts, but if you had a third or fourth, you would still take the sum of the products of the coefficients. Okay. All right. So now let's talk about unplanned comparisons because you can go about this in a couple of ways. So, as I said before, when you're conducting multiple analyses on the same dependent variable, which family of tests, the chance of committing a type 1 error increases, right? All right. So, Bonferroni corrected pairwise t-tests. This is a pretty simple procedure where you essentially adjust your alpha. So here, your Bonferroni correction is equal to your original alpha over the number of contrasts, which is C, okay, or number of tests. So this is really conservative. And so since it's conservative, it increases your potential for type 2 error. It reduces your power, okay? So know that. So it does reduce your power, but it controls your experiment rise error rate, which is a good thing. So you kind of have to weigh the pros and cons. I would say it's best to control that experiment-wise error rate, okay, to be a little more conservative. So here, just alpha. So usually 0.05, but not always. It depends on your test and what you're interested in, right? Okay, 0.05 or whatever your alpha is over that number of contrasts. All right, so that's your new alpha. And so your t-test, when you carry out your pairwise t-test, you would utilize that new alpha to compare your p-value to. So it is more conservative, okay? All right, so that's a really common way of going about post-hoc testing. Perhaps the most common is Tukey's HSD. So you may have seen this in papers where we utilize Tukey's HSD to determine whether there were differences among all groups. You may have heard it called the Tukey-Kramer method. You may have heard it called Tukey's post-hoc test. All of those are talking about the same thing. And that is an unplanned comparison situation where you're comparing all possible comparisons. Okay, so for unplanned comparisons, Tukey's, and so most people use Tukey's, and here's why. Because it can control experiment-wise, it does control experiment-wise error rate, but it's still powerful. So when you're doing Bonferroni corrected pairwise t-tests, right, I told you, it reduces your power. It's more conservative. So a lot of folks go with Tukey's, okay? And here, your Q statistic is the test statistic, okay? Usually, like in R, you get p-values, and you can utilize those p-values to tell you whether your comparisons are significant or not, your pairwise comparisons. But I did want you to know that that's a Q statistic. Other kinds of tests that you might see that we're not actually going to learn in this class, the student Newman Cool's test is also popular. It's more powerful but less conservative. But it is a post hoc test that some people utilize. So if you see student Newman Cool's or SNK, that's what they're talking about. That's a post hoc testing mechanism. All right. So these involve testing all possible combinations. Okay, cool. So which to use? Well, it depends on what you want. Okay, and I'm not teaching you sequential Bonferroni. I'm not teaching you false discovery rate. I just wanted to put them in here so that you can see them. So when you see these in papers, or if you see it on, if you see it when you get to graduate school or medical school, you'll know what they're talking about. So if you're interested in specific planned comparisons that you're deciding a priori before you go out and get your data, when you're coming up with your experimental design, then you can utilize orthogonal planned t-tests. Okay, if you get your data and you get an ANOVA that is significant and you want to do unplanned pairwise contrasts, then you can use Bonferroni corrected pairwise t-tests where you adjust your alpha, that's that Bonferroni correction based on the number of tests you're wanting to run, and then run your t-tests. Okay, if you're interested in all possible contrasts, then you can run Tukey's. Okay, you may also see sometimes though a sequential Bonferroni or false discovery rate. Those are essentially just showing you where contrasts lie. Okay, very simply, that's what that is. So let's show you an example. You're going to see more examples on Thursday with your tutorials or whenever you watch them. I guess you can watch them before. But here's an example from a paper from 1997. So, question. Plants are often connected by roots via mycorrhizae, which are fungi associated with roots, and there are two kinds. And if you've taken ecology or bio 2, which is, I think, everyone in this class, then you know that those are ectomycorrhizae and arbuscular mycorrhizae. Sorry. You know me. Okay. I get distracted by fungi. What can I say? Okay. I really hope nobody turns this stuff into memes. Okay. Ooh, or you could. Bonus points. Anyway, so plants are often connected by roots via mycorrhizae, allowing for resource exchange. All right. Could shade impact the extent of resource sharing? To find out, researchers compared the net movement of carbon from birch to fir trees in different levels of shade. So, think about this. The first thing you need to do, we don't have the data here. Obviously, you would look at your data, but you need to think about, what is my question? What's your research question? So, what is my dependent variable? So it seems, let's see, carbon movement, right? Okay. Carbon transfer, right? And then your independent variable are your levels of shade. And so how many levels of that independent variable? You have your treatments here. So there are 3 levels, right? So deep shade, super shady, partial shade, or what I like to call slim shady, kill me, and no shade, okay? So those are your 3 treatments. So there are 3 levels of this factor. Here are the descriptive stats, okay? So your descriptive stats, that can help you look at some of the trends in the data, but here are the results of the ANOVA. Note that it is not a full ANOVA table, and therefore I don't like it so much. I mean, it's just better to report your, it's nice to see your sum of the squares and your mean square values, but you can see your mean square group. Now, remember, this is your mean square group value. This is your mean square error value, right? Because the analysis of variance is looking at the ratio of those sources of variation. We're between groups versus within groups, right? Okay, so here's your F statistic, 8.7. Okay, that's pretty good. That's pretty high. And if you compare it to a critical value table, I can just tell you off the top of my head that would be with your degrees of freedom, that would be significant. Also, there's a p-value down here. So the p-value is less than 0.05 because we can reasonably assume an alpha of 0.05. So we reject the null hypothesis. The amount of carbon birch transferred to fir is not the same among deep shade, slim shady, and no shade. So where are the differences? Okay, so these folks, this example was with a Tukey's HSD, which is what you will most commonly see in the literature, though you will sometimes see orthogonal plane contrast and Bonferroni corrected pairwise comparisons, pairwise t-tests. False discovery rate seems to be getting more common, but Tukey's is what you're usually going to see and what you're usually going to run and what I'm going to teach you to run, okay? All right. So this will actually really help you when you're reading papers, because sometimes people will come to me with like graphs and they'll say, well, what do the letters mean? Well, you're about to find out. So here are these are the comparisons themselves, okay? And what I want you to pay attention to, these are the Q values. Q values in a Tukey's test, that's your statistic, right? Your test statistic, your critical value here, and then the conclusion. Now, in R is sweet and gives you p-values too. So I think just p-values, but R makes it very easy to intuit what the results are. Okay, said R twice, sorry. So here we're comparing deep shade to no shade, because remember, Tukey's compares all comparisons. So deep versus none, all right? So same rule as with any of your statistics. If your statistic is greater than your critical value, then you reject the null, and there is a difference. Okay, so deep shade versus no shade, that critical value is larger than that, that statistic is larger than the critical value. So there is a difference between deep shade and no shade. Okay, deep shade and slim shady. Again, not as great, but you do have a difference because your Q value is greater than your Q statistic is greater than your critical value, so you reject the null. Okay, cool. And then here, partial shade versus no shade, there is no difference because this is smaller than your critical value. Okay, cool. Oh, you guys, I made a mistake. Hey, River, will you bring me my computer charger? Thank you. My computer's getting low, and I usually have it plugged up, but when I started this, I had full battery, And then I kept wanting to change things and stopping. Yes, this is like take 2 of this. Thanks, buddy. Thank you. Will you plug it into the wall there? You want to see his hair? Show me your hair. He's like purple and green hair now. Look how cool he is. All right. All right. That would be so helpful. What? Needs to stop. We're too far in now, guys. Thank you. Good job there. All right. Here he is. Okay. So, again, so here are where our differences lie between deep shade and no shade and deep shade and partial shade. Partial shade and no shade do not differ. Okay. Yay! Okay. So here is a figure from that paper. So you can see, again, deep shade is different from partial shade and it's different from no shade, but partial shade and no shade are no different. And now you see this graphically, right? The way that we show this with a significant ANOVA, the way you show your post-hoc results is with letters. So that's what those letters mean, is essentially results of post-hoc testing, or multiple comparisons, pairwise comparisons. Well, pairwise or multiple comparisons. So here is showing your significance groups. Okay, so if you have, A is different from B, so deep is different from partial. Okay, so A versus B. Okay, and it's different from this one, but these are not different, so they'll be the same letter. So A versus B and A versus B again, right? These are the same. This one is different, this group. Okay, pretty simple. Now, one special case that you need to be aware of is, for example, let's say maybe B was higher and the error bars were wider and there was not a significant difference. There was a difference between, let's say there was a difference between deep shade and no shade, but not between deep shade and partial shade, okay? And not between partial shade and no shade. In that case, this would be A, and this would be B, but this would be A, comma, B, because it's a member of both groups. Okay, and that's what I'm saying down here. So if you see A and then A, comma, B, comma, C, that means it's not different from any of 3 other groups, right? And then you have a group B and a group C. If, for example, you had 4 levels of your independent variable. Okay, all right. So that's how you represent significance graphically. That's how you would interpret that. Your book talks a little bit about fixed and random effects, and I tend to do that earlier in the semester, but I realized I have not introduced that very well, very much. So I just want to make sure you understand what fixed and random effects are. So with fixed effects are treatments that are chosen by the researcher, whereas random effects are simply a subsample of all possible treatments. Okay, so fixed effects are things that you can really control. It's not a random subset of possible treatments. So certain drug treatments, certain seasons, that's a fixed effect, right? Seasons, certain diets, yeah, anything that it's like, this is what I'm interested in and nothing else, and I've accounted for all of it in my independent variable. Those are fixed effects. Okay, random effects are essentially random samples from all possible treatments. All right, so places, just like stream sites. When in my own research, when we go to different streams, that's random. That's a random effect, right? Individual people, usually when you're dealing with natural phenomena or anything like, usually not all observational studies. That's not true because season is often incorporated into observational studies or maybe a part of that. But if it's a subsample of a larger group that could be possibly a treatment, that's a random effect. Okay. Okay. So when you're thinking about random effects, you're not interested specifically in particular groups and only those groups, right? What you're trying to do is learn as much about the variation in a population as possible. Okay, so That's why randomization is so important, because most of the time you're dealing, not always, there are fixed effects like certain dosages of drugs, you know, if you're only interested in those dosages of drugs or what have you. But for random effects, that's why randomization is so important, because you're trying to understand and evaluate essentially how much variation is from among the groups versus within the groups, your ANOVA, right? Okay, so that's when you see people talk about random effects versus fixed effects, that's what they're talking about. All right, cool. So that's all I have. Oh, wow, 34 minutes. Maybe I should talk about more stuff. That's really all I had to talk about though. So um, the next video, if you have not already, you can watch the tutorial on how to run a t-test in R, and you should like do it with it. You'll have to stop the video and try it, but if you come up with any, what are those called? Errors, yeah, let me know. And you can do your ANOVA too. There's an ANOVA tutorial that's also up. That's just for ANOVA. There's no post-hoc testing in there. The next tutorial that I'm going to put up before Thursday, which is technically for Thursday. So this is your Tuesday class. And your Thursday class is, it should do it on Thursday. I shouldn't do this. Thursday class is on multiple comparisons. So how you're going to do that in R. And all of this will be on your next exam next week. So let me know if you have any questions. And I want to remind you, Thursday at 8 a.m., well, actually, Tuesday at 8 a.m., but you may not watch this till Tuesday. Both days this week, we're going to have group chats. The first one is just a check-in. I did one with Bio 112 today. It only took like, I don't know, 15 minutes, about 15 minutes. We just talked, and we talked about how tests would work. People were asking questions on the chat. So if you can dial in tomorrow, awesome. You get 2 points just for showing up. And then Thursday, you get a point for showing up. It'll be just like that every other Thursday. You'll get a point for showing up and 2 points for actually participating. So, all right. If you have any questions about this lecture, you can post them in the discussion group. And also, we'll talk about any questions you have at our live Q&A on Thursday, just to be sure that we absolutely cover all of your questions and you have the opportunity to see these answers in multiple formats. So I will see you hopefully online.